This is the page that I was telling you. If you go here, the link is in the definition. I will share it right now, but it's this one. You will find at the very bottom there is a short explanation of what you must do in Kangaroo to have a realistic simulation that you can pass to Caramba 3D or Millipede or whatever in order to have some to avoid discrepancy between the shape that you are going to analyze and the actual final result. Okay, and at the very bottom you will see this image. You can click on it and you will download this cluster that basically allows Kangaroo to perform a realistic simulation according to the material that you want to use and to the actual geometric properties of your structure. So let me, I don't even remember where this component is actually, so I'm going to download it myself. Yes, like this. And I'm going to grab this from the download is here. Okay, so this is the definition that you are going to download. I'm going to place it here in our folder. So let me drag it and let me also open it so you will see Kangaroo Young model. Yes. So it's a very stupid script, but nevertheless it allows creating some realistic simulation in Kangaroo. So it's very easy to work with this. So you need to provide the elastic modulus for a specific material that you want to simulate. So, for example, you see here you will find a list of elastic modulus divided or classified by material. From soft material like rubber up to extremely rigid material like iron and so on. So according to the material that you want to simulate in your Kangaroo system, you just plug one of these inside this first number container. This is going to be the elastic module in gigapascal. And then you must provide the area of the cross section of the elements that you are going to simulate, and the lines that you want to use as elements in your Kangaroo system. So in order for Kangaroo to use this real elastic strength, which is the value that is going to be output by this one, you must do something like this. Let me work with, for example, let's say you want to use iron bars or eventually structural steel, okay, something like this. So I take all of these things, including the gigapascal elastic module, copy it, close this, and I'm going to paste it right here. So it's here. So the only problem that you have with if you want to run a realistic simulation with Kangaroo, this is something that I also told you yesterday, I think, is that the simulation becomes extremely slow, but very, very slow. And we are going to see it right now in action. So this is the Kangaroo solver. These are the strengths or the goals from Kangaroo. So I'm going to take all of these things here and move them to the right in order to make room for our things. I will not use this component here, and I'm going to tell you why in a second. Okay, so let's move everything here to the right, and let's reactivate at least the Kangaroo simulation. So here, this thing here. Let's wait for this to react. Okay, that's it. Oh, there is the reciprocal structure that let's deactivate this as well. Okay, so basically, oh, and also the anchor point. I need also to reactivate the anchor point, or if this is not going to work at all. So what we have from this simulation is this thing here. We can reset it eventually, and we can run it again. It doesn't matter. But what I'm going to show you is this. This is the simulation running with a, well, I would say, fancy strength as regards the elastic property. And you see that the system moves and reacts quite in real time. So it's pretty fast. It takes seconds to get to the final solution for Kangaroo in this case, even if the mesh is already quite dense in terms of resolution, but you see that it's pretty fast. Okay, so remember that after 10 seconds, we already got to this result. Okay, so I'm going to reset this. And what I want to do right now, I want to work with real elastic strength. So I want to simulate a specific material for this structure. In this case, I can use the edge length component. The only thing that I need to change is the strength. Because what I'm telling with this edge length component is that the whole mesh, meaning the whole set of edges of this mesh, must have a length factor of 1. So by themselves, they don't want to either stretch or compress. So they want to maintain the original length. And they are as strong as 1. Now, this 1 is a scalar value. It has no meaning, basically. It doesn't correspond to any material. The only reason for this value is that it's balanced with respect to the default strength of other goals. So, for example, anchor points have a strength of 10,000, because normally they must be stronger than any other force that you use in Kangaroo simulation. Okay, so that's why you have this kind of balance between the strength of the elastic forces and the strength of anchor point and so on. But now I want to define the strength according to a specific material. So I will take these objects here and say, okay, so the elastic module for structural steel is 200. And that's the first parameter. And then I also must define what is the area in square meters for our beams or our frame elements. Remember that we are working in meters, even if it says millimeters. That's because I didn't open any file. So we are working in meters. I don't want to scale anything. And I need to provide the area. So let's say that my generic frame has something like let's use a square cross section. So it's going to be like 4 centimeters by 4 centimeters. Okay, so this is going to be the side. I'm going to basically multiply this by itself. And this is going to be the area. So the area is going to be quite small if you work in meters. So it's a very small value. And we also need the length of these objects. Now let's move this inside our working area. Remember that we are working to define the strength of these springs, actually, of these fibers, of these elements. Okay, so we have the diagonal meshes. Independently from naked edges, clothed edges, we must define the length of each of these lines. Okay, so what we can do is take the mesh edge component like this. This is going to provide us naked edges and interior edges. Okay, now due to the fact that we are working with a diagonalized mesh, we should double check that naked edges and interior edges all together correspond exactly to the amount of edges that we have here, because as we have fake naked edges on the inside, this makes me think that there are 2 overlapping naked edges, because else they wouldn't be naked, right? So we should double check that this is actually not happening. But in this case, I'm just going to show you how this process works. So I'm going to take all of these lines and merge them inside one single line component. And I'm going to pass all these lines to the line um, container here. Okay? And that's it, because this is already receiving all the inputs. Now, what does this component contain is a simple mathematical operation, because the elastic strength of a specific element with a specific material is basically the elastic modulus multiplied by the length, is the elastic modulus multiplied by the length, and the result divided by the area of the cross section. So it's basically E multiplied by L divided by A. So if you think about it, the elastic modulus is actually in gigapascal, but during this expression, inside this expression is you must work in Pascal. So this value gets multiplied by 1 billion. Okay, so it's 200 billions Pascal. Okay, multiplied by the length, that more or less it's 1 unit, so it's 200 billions divided by 0.0016. So the actual strength that we get from here is extremely high value, as you can see. So if you want to simulate a mesh or a structure made up of structural steel, you must plug this value here as the strength of this object. Now, if you do this, as I'm doing right now, Kangaroo is probably going to hang a little, because this is not exactly correct. We are assigning, let's say, a certain amount of strengths, which are defined by element, to the mesh. But we have one single mesh and hundreds of elastic strengths. And so we are actually here producing hundreds of different mesh objects, each one with a specific elastic strength. So this is not correct. So when you work with this, you cannot work with edge lengths, actually. Because you see, in this case, we are obtaining 331,776 different meshes. Okay, so we cannot do this. The proper way for working with this thing here is to work not with mesh, well, what is it? It's this one. Okay, it's not working with edge lengths that assign the same elastic property to the whole, all the edges of a mesh, but with a length line that assign a specific elastic property to each of the lines. So I grab the lines, convert it into elastic object, and each object, which has 576, will receive its own elastic strength, like this. And in this case, the length, if you don't provide any value, the length, the rest length will be exactly the length, initial length of these lines. So everything is back to normal. And you plug this instead of the initial elastic force. So you work with this cluster according to the proper elastic modulus, and you substitute the edge length that operates at the mesh level with length line that operates at the element level. Once you do this, you have an extremely stiff set of elements in this case, because they are reinforced steel. And the only problem that you have is not that it doesn't work, actually, but it becomes extremely slow. So take a look, for example, I'm going to concentrate on this mesh here. Take a look at this mesh. Now, this mesh is actually already converged. And the reason why it already converged is because we are applying a load of 0.10. Now, if you work with a real elastic strength, you also must work with real loads, because 0.10 as force has no power to deform such a stiff network of structural steel elements. And so you must apply real loads in this case. Also, another thing that can happen, as the strength of these elements is basically the order is 200 billions, while the anchor point are only 10,000 strong, then if you apply a load capable of deforming the structure, probably the structure itself will start to fly away, because the anchor point are not strong enough. And so if you want this object to stay anchored to the ground along the outer edge, you must also provide a proper strength for the anchor point, like, for example, 200, 1, 2, 3, 1, 2, 3, 1, 2, 3, which is not possible in Grasshopper, that only allows a maximum of 100 millions. So the risk is that this thing is going to fly away. And also, let's try to apply a load in real life scale. So this can be in the same unit system that we are using, which is Pascal, meters, and so on. Force is represented in Newton. And so we must provide here a strength for this load in Newton. And so let's say that we want to apply a load of 500 kilonewtons, like 500,000 newtons. Okay, positive, so it's going to move the structure upward. Eventually, if we go here, we should start to see that this thing is starting to move. You see, it's running, but see how slow. Okay, so yes, you have a simulation running right now. It's actually pretty fast if compared to what happens with a real structure, with a real consistent amount of elements. But nevertheless, before this gets to a converged status, it's going to take a while, because the final oscillation, the final vibration around the equilibrium status are going to be very, very slow. Okay, and also you must double check that you don't have a displacement for the anchor points. You see that this object has already lifted up a little at the corner and around the edge, the border, because the anchor points are not strong enough. Okay, this is, you can also, let's say, omit this kind of observation, because normally it's not that evident. Okay, but you must take this into account if you want a realistic behavior for your system. Now it says converged, so everything is already stopped calculating, and then you can reactivate Caramba 3D. And of course, in this case, I am using as a material concrete, but I cannot use concrete anymore. You know, so everything must be, let's say, in line between the two parts of the definition. Okay, so the cluster, you can find it in my web page. The link will be here in the definition. I can also, if you want, I can also write it down right now in the chat, so you can have it already, and you can download the cluster. Is at the bottom of the page, and you can use it like this. It's very simple actually. It's just a multiplication or an expression basically contained inside this cluster. Nothing special, but you see that as a consequence, you get a very and extremely slow simulation. Okay. Actually, you might see it from this image. This image is a structural analysis that I conducted on one building here in Mexico. And it was made exactly like this. Kangaroo with real elastic strengths for the elements, and then Caramba 3D structural analysis. So I hope this answered your question.
Yes, it answered my question. Thank you so much.
Perfect.
But,
you're welcome.
Just one more doubt.
Yes.
How about like the division of number of meshes? Like as you give more meshes, the resolution is much better.
Sorry, I
Also,
still hear you quite far.
Is it clear now?
Yes.
Yeah. So if we give like more mesh division, and if we give less strength itself, the deformation will be much higher. Like
Well,
in a lot of cases.
in theory, yes, but keep in mind that this is exactly what happens when you don't work with real elastic strength. So the amount of springs or elastic things that you have inside the system affects the final deformation, of course. But if you tell this system that all the elements that form the network of beams are so stiff as this value here, it doesn't matter if you have 10 beams aligned like in this direction or 100 beams aligned, because the global length will be exactly preserved. So this
Okay.
is what happens when you work with real life strengths.
Okay. Okay.
Thank you.
You're welcome. Okay, just so that this thing is going to work smoothly without being too slow, I will just disconnect the strength from this length line. And I think that's pretty it, because that was the only thing that was. Oh, you see, for example, right now I have eliminated the elastic property, basically, or got back to a very soft body, actually, and I'm still applying 500 kilonewtons to this object. So the deformation is now something like this. Of course, there is a scale factor that is not being respected. So I will go back to 0.10. But remember that if you want, you can change this. If you change the strength, if you consider the real strength, you can also consider the real load. As the anchor point, you can still maintain this value. The important thing for the anchor point is that deck power must be stronger than the other loads. So in this case, this is going to fall down, oscillate around the equilibrium phase. You see that it's actually bouncing up and down because it was quite far from the origin. It's better to reset and make it run again. And so that's it. So I will leave this like in this configuration. I will try to organize things a little better, and then I will share this definition with you as well. So that said, let's move on. There is also, yeah, 3D. There is also this version here that we are going to skip, actually. This is the same thing, but with millipede. Okay. Also, millipede can work for performing a shell optimization, but you must work with FE mesh, of course. The rest is basically the same. Okay, so it doesn't change anything. You have also stress line, mesh visualization. It works exactly the same as we already saw. There is also here some quick example of eigenmode analysis, like in terms of vibrational analysis for the shell structure. You can simply try to play with it a little, and eventually we can discuss this in private if you are interested in understanding a little more about this part. So I will go directly to topological optimization. We are going to see three things. First one is 2D topological optimization with millipede. Then we will switch to 3D topological optimization with millipede as well. And then to 3D topological optimization with topos, which you will see is going to be a little better than millipede. Remember that millipede has been discontinued, so topos should be your natural alternative to this millipede software. And also you will see that topos is quite faster than millipede. But anyway, let's start from the first thing, and I need to open also the file, because there are some things that are imported from the actual Rhino file. I will internalize this value, so the definition that I'm going to share will be independent from Rhino. And what I'm going to use is this thing here. Okay, so let me hide this. So I'm simulating a two-dimensional region, which is this rectangle here. And I'm going to, let me turn this on. I hope that it was not, yeah, it's running actually already. So you see that the topological optimization has already started and ended as well. We will discuss this in a while. But the result is this thing here. So basically what we have, let me hide this. So in order to understand what we have in this area, how this thing works, it more or less is the same as the structural analysis that we have performed previously. The difference is that this analysis here, this topological optimization process, focuses on the stress lines, basically, and tends to optimize the usage of material, um, condensing the material along the stress lines. So where you have more concentration of stress inside the region, inside the boundary region, then the software assumes that in that areas you need material, while in the remaining area there is no need to fill the body with material. Of course, this is only valid under certain circumstances, like for example, you must work with isotropic material or eventually compression resistant material and so on. Okay, but nevertheless, the method is pretty interesting. So what do we need in order for these things to work? First of all, define the boundary region. And in this case, is the circular area that you see here. Okay. Then inside this region, you can define a load or load areas, which is basically here. We are applying a load at the center of this membrane. Okay. And this load is going to be 1,000. Remember, here you can work in Newton per square meters. Okay, so we are applying a load in the y direction, but actually negative y direction. Okay, so you can decide in which direction you want to work with the load, and we are applying this load only in this area. Okay, not in the surrounding part. And we have support regions. And support region, in this case, once again, they are all set to true. So these are fixed support. And all these little square are support regions. And that's it. Once again, we have the body or the geometry, the load areas, and the support areas. Okay, in 2 dimensions, because what we are going to do right now is to perform a 2-dimensional topological analysis. So if we go to, what is it, millipede, there is this topostruct 2D. So everything you want to analyze in terms of 2-dimensional topological optimization, it's inside this group here. Well, except from some stock things like support type and material and so on. But anyway, this is the group of commands that allow working for 2-dimensional topological optimization. Okay, and so the topostruct 2D model, you can find it here. And also the solver is a topostruct 2D solver, which is this one. Okay, so don't mix up things because they don't work. Okay, so this is actually, as we already saw with millipede, this is actually merging together all the elements for our FE model. So the body or the geometry, the load, the support, and so on. One important thing here is the resolution. So X resolution is basically how dense you want to be the representation of this, well, actually mesh object in the end. So it's always mesh object when you do this kind of analysis. Okay, whatever software you use, it's always mesh object. The reason is very simple. NURBS objects are mathematical object, theoretical object, perfectly smooth and continuous. So, for example, a mesh line, a NURBS line is formed by an infinite amount of points. And so if you pretend to calculate stress along a NURBS element, like a line, you will need infinite amount of calculation. But if you create a discrete representation with a mesh object, then you have a specific number of steps, and then the number of calculation is finite. So that's why you need to specify this resolution. This is a pretty high resolution for a millipede system. It's already quite dense, the mesh that you get. Nevertheless, if you want to get a smooth representation and a smooth result, you cannot work with very low resolutions. Also, because this resolution is actually distributing a set of calculation nodes inside this area. And when you work with very small areas like this one, this support area, it might happen that one node falls out on this side and the next node falls out on the other side. And if this happens, this area will not be considered as a support area. So in this case, if you work with very small areas, you must increase the resolution, which means that the calculation will be extremely slow. Okay, but in our situation, you see that a quick check is by activating the preview of topostruct 2D model, and you will see that the load region are in blue. The orientation is negative y, as you can see. So the lines start from the node and go in this direction, which is negative y. And these are the support. when you see these little crosses, red crosses inside the support area, it means that they are going to be taken into account. If I decrease this value, eventually some of these little square will not be filled with any node. And then there is the optimization iterations. As this is a topological optimization solver, the more iterations you define here, the more precise is going to be the result. So initially, what I'm going to do, I'm going to decrease this value. And in the end, you have the usual thing. I mean, you can visualize the result in several different ways. And I also made some elaboration of this, and we will discuss this in a while. What's the idea, for example? The idea, in my mind, at least in my distorted mind, was to simulate that in this case, we have some, imagine that this membrane here is a ceiling, right? So imagine that this is where a big column lies underneath this, this ceiling. And this is where the membrane is anchored all around, right? So what I wanted to define was what are the stress lines inside this membrane in order to give more thickness along this stress line and to make a lighter ceiling on top of this column. Okay, so this is the thing. And I'm applying actually, well, it's the opposite. Sorry, my bad. These are columns because these are the support. Okay, and this is where I'm applying the load. So something it's applying a force in this point. Okay, so if we run the simulation, let me decrease the number of iteration. If I set this to 1, for example, we have only one step, as you can see. Well, this is the initial. You see this little window opens up. This is the calculation going on from Topostruct to the solver. Okay, so you would see a progressive refinement of the solution, well, like with these small images here. With one single iteration, Millipede is not capable of calculating any stress distribution. Okay, if I start to increase this up to 10, you see that already with the second iteration, you already start to see some distribution, some difference. And 10 iteration is already enough to define some kind of nice stress distribution along this membrane. If you increase this to 20, also micro areas, micro region will start to appear. And also there is a progressive refinement that also eliminates some whitish areas inside this region. So you get this kind of flower-like structure where you see that the stress lines are flowing from support towards the center where the load is placed, but in a very elegant and thin line structure. Okay, so let's say that we stick with 20 iteration for now. It's already a good detail for our simulation. And then you can visualize things in several different ways. There is 2D cells result. Actually, this is only displaying with frames what is the orientation of the stress lines inside this membrane. Okay, so I have used here a vector display in order to take the principal stresses, which are vectors, and visualize them with some controlled amplitude in order to see how the stress flows inside this structure. Okay, so this is visual analysis basically. Two node results, also visual analysis. These are the nodes that Millipede has taken into account to perform the calculation and to run the simulation. These are starting to be more interesting previews. So you have ISO contour lines. So this ISO means that the stress inside the structure is equivalent all along these lines here. Their resolution, they look a little crispy and you know, like polylines. It depends on the resolution of the system. So the initial resolution that we set here, the X resolution, also affect this geometry here. But nevertheless, it's something that you can also adjust with some further operation, like rebuilding this curve with enough control points, but with degree 3, if you want degree 3, sorry, if you want a more smooth representation of these contour lines. And then you have the 2D mesh results. Now, in this case, you see that we have a colored mesh. The color depends on the stress, of course. It is actually exactly the calculation that Millipede did in the small window, as you remember. The resolution that you see is quite bulky because 50 SX resolution is not enough to have a more smooth detailing. If you want, I don't remember what was the actual resolution, but as Millipede is running quite fast with this system, I can also exaggerate and bring this down to 80. You will see that there are more details appearing also in the black areas because they are subtle stress lines, like secondary stress distribution inside these black areas. The higher this value, the more resolution you get from this representation. And now, once you have this, it's very nice to have this kind of result because this is actually a mesh. Okay, you can deconstruct the mesh. Oh, and by the way, you can also consider deflection, like we already saw in many other occasions. So let me quickly show you what happens with deflection in this case. I think that I should turn some things off here. Maybe we need to tweak this deflection differently, because remember that there is always max deflection. I don't know why I didn't implement here the division method. I do recommend that you do this because it's difficult that you have a balance between this value and the actual deflection that happened in the system. Okay, so you see that maximum deflection is very, 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 very small. Okay, so I do recommend that you always use the same method. I'm going to implement it right now. So a division and a slider between 0 and let's say 10, like to exaggerate. So let's divide this by this. Once again, we will be dividing a small number by a very small number. So this result is going to be big. And so eventually, in this case, we will be able to observe some kind of deflection occurring. Let me deactivate this, so just in case it's producing some kind of, yeah, you see that now deformation is actually working. And as we are working with a vertical load along the y direction, then this is the deformation that's happening. It's not falling down. I should use a negative z vector if you want, but this is what happens in terms of deflection. Okay, but it's just changing the direction of the load. It's not rocket science. And then here, for example, this is an interesting further development is if you take the mesh that's coming out from the simulation and deconstruct it, means you explode it, you get lots of information, vertices, faces, but also colors. So the concept, the idea here is to use the color in order to change the thickness of the mesh. So you see, for example, that here we have the initial vertices. They are being exploded into their coordinates x, y, and z. And it's not clear because there is a wire that's running right this, but we are only using the x and y component to define a new point. And this point will have a z coordinate that depends on the color, on the grayscale tone of the original mesh. So basically what happens is that when you have white, the mesh is going to fall down. And when you have black, the mesh is going to keep the original height. So basically what I'm doing, I am increasing the thickness of the mesh with correspondence to the white or to the light gray areas. Okay, and so if you take a look at the mesh, this is the actual result. And you can also smoothen up the mesh a little in order to have this kind of nice result. And of course, This means that if you consider this as a solid object, and then eventually you will have a variable thickness that it depends on the distribution of the stress lines inside this membrane. So if we place columns where these points are, and if we apply a load here at the center, this thickness here in a compression resistant material, of course, is going to be good for bearing the load that we apply in this area on top of the membrane. So that's the idea. Okay. Now, there are many applications of this thing. Eventually, you might have seen some application for product design also with, I don't know, changing the thickness of the surface of a chair according to the loads that you apply in the sitting area. It's basically the same thing. Okay, it doesn't change anything. So this is two-dimensional topological optimization. It's very simple, actually. If you think about it, it's always the same, as we already saw with other simulations. You just define the system, you define the loads, supports, and then you run some simulation, and then you evaluate the result. Another interesting result are the stress lines themselves. So you have a complex set of curves in this case. Of course, there are two principal stress lines. And you also have the contour lines that somehow mimic one of the two direction, but they have a different meaning, right? So these are iso lines, iso curves. So the stresses are equivalent all along these lines here. And so you can also use these for other applications in terms of design, of course. Everything clear? Do you want to further discuss something? In the meanwhile, what I will do, I will quickly change a little the support condition. So, or eventually what I can do is simply switch things. So let's say that I want this to be the support, and I want this thing here to be the load region. So I'm inverting the situation right now, and I want to double check what happens in terms of structural analysis. And of course, it was quite easy to foresee. We have an inverse situation right now, and so we can also display the result like directly with the deformed mesh. So this will be the column, and then will be this variable thickness mesh. It's very nice to play with this because you have this kind of veins running through the membrane. And of course, everything here is like for representation. Of course, there is a variable that I'm not considering at all, which is what thickness do I have to assign to this mesh. It is actually defined by this slider here. So the mesh falls from 0, which is black areas, to -4 meters, which is the white area. But this is not necessarily so. So it depends on many aspects. Essentially, it depends on the material and if you are what type of structure you are going to create right here. But this is only based on stress lines. So it's just like for a pre-visualization or previous step for the design process, structural design process, because it's for us in this moment. It has no meaning to make this fall down to -6 or to -0.73. So it's absolutely equivalent. The important thing is to understand how to place material inside this object, okay, in order to make it resistant to the actual load and support condition. So another nice feature that we have available in Millipede when we are dealing with two-dimensional topological optimization is this stress pattern. This is actually a component that doesn't work alone. It actually creates a pattern that can only be used next in order to create some visualization or some design. You see that it is this component here. It doesn't produce any preview actually. So if you turn this on, you see nothing in our model. But nevertheless, it's very interesting to work with it, because actually what it does is create is take the 2D topological analysis and create basically the basis for a pattern definition. So this component itself doesn't draw anything. It just produces a thing which is called a system that you can use with another component that is actually creating a pattern according to this system. So in this case, for example, I am based on this system, which is laid on top of the actual stress lines that are calculated during the topological optimization. You can choose, for example, whatever pattern you might want. Actually, I'm using an hexagonal pattern. You must provide the pattern must be lines or curves actually. So you see the parameter icon of curves, and I am just exploding the hexagons, and then I am removing the duplicate lines in order to use only, and I'm also adding these lines from the center of each cell to the vertices, so in order to have a more complex representation for this pattern. And then this component is actually laying this pattern according to the stress lines of along the surface. You can decide the density. You can change the density of this pattern by changing the omega pattern. So if you increase this value, you will have a higher density for the pattern. So if I decrease this to 0.2, you will see that the pattern will become less dense. In a while, it's quite slow as calculation. So you see the result. But the interesting thing is that this design is actually following the stress lines along the surface. And let's switch to 3D topological optimization, which is going to be basically the same. Oh, it was already on, so it's going to recalculate eventually. Oh no, because I deactivated the solver. Perfect. Smart move. So and now we have quite a simpler system. 3D topological optimization with millipede might be a little tricky. So you will see that it's quite difficult to come to the desired result with millipede. That's why I also put here the same topological optimization, the same system, but with Topo. So we are going to take a look at this also from Topo's point of view, which is going to be quite interesting. And you will see that that is going to work smoothly. So what we have here, once again, building the system. So 3D boundary region, which is the body that you want to evaluate and optimize. And in this case, it's just this object here, but it can be also a union, a Boolean union of different solid objects. Then we have, and you can define, for example, if this volume that you are passing to the 3D boundary region is a void or not. So you can also, for example, create a C object like this by adding another 3D boundary region, like another box, which lie here at the bottom, and define this second box as a void, and plug it together with all the other component here into the model components. So the limitation that you have in millipede as regards the 3D topological optimization process is that the limitation is that you must work with boxes. So you cannot optimize, for example, topologically very complex shapes. Like let's say you want to perform a 3D topological optimization for this kind of thing. You cannot do this in millipede, but you can do this in Topos. Okay, so millipede is limited to a box-shaped object, be them like field volume or void volumes, okay, which get rested like in a Boolean operation from the field volumes. And then there is here the 3D load region. So I'm applying a load in these two points here, or these two areas actually. And then there is the support region, which is just this one here. So with respect to the shape of the object, We are just anchoring the object here at the lower bottom right corner. You cannot do this with the millipede. You can do this with the dome. You can do this with topos as well. So also the dome object, Andre. So everything that is not a box shape, you cannot do this in millipede. You must do this in topos. So so basically, our system is this kind of cantilever beam, maybe, with fixed support here, and two loads applied more or less at half the length and at the tip of the beam. Okay, and so it's as usual support type, 3D support region. These are things that are basically once again support type is from the stock here, but now we are in Topostruct 3D, and so you see that you no longer have 2D density, 2D load, 2D support. You have 3D density, 3D load, 3D support. We are using only load, support, and boundary region. Then there is the Topostruct 3D model. I do invite you, when you build this kind of systems, don't rely only on the preview of the boxes, but always turn this on in order to understand if millipede is already detecting the loads and the support. Okay, because if you don't see any of this, then you might have some, let's say, weird behavior during the simulation. One thing that's important when building this kind of system is this. When you have these objects here, 3D load region, you know that in model components, but I think this is something that we already said, but model components must receive a list. So now in my case, I only designed some boxes, right? So I know that this is going to be one single element. This is going to be two elements in one list, and this is going to be one element alone. Okay. Nevertheless, when you merge these things all together, just be sure that here you are receiving a list. So either you flatten the input, which is something that I do not recommend, because remember that flatten is not visible in millipede component, or you flatten before connecting these to model components. And remember to do this, because if this receives a tree, a data tree, the calculation is going to be quite heavy, and so Grasshopper and could hang or crash. Okay, so I'm going to place here a small note, like simply flatten. So remember this, because else you are going to have, I think I have to get rid of this. Yeah. So remember this, because it's very important. Okay, so flatten here. Okay, and then we have X resolution set to 60, and this time I'm setting the resolution quite high. You see that many nodes fall inside the load and the support region, right? So hypothetically speaking, I could also decrease this value, because I already have enough nodes inside these regions. But in this case, remember that this resolution here also affects the mesh result, like we were observing already into 2D mesh results. Okay. Now we have a 3D mesh result. So the higher the resolution, the best will be the representation of our final optimized topology. Okay. If you have a low resolution simulation, then the mesh could also come out very bulky or without details, or not capable. For example, I can imagine that if I look at this system, I can imagine that as I'm applying the load here, and I have support here, I can imagine that more or less I will have some stress distribution like this, right? And so I can imagine also that I will need some material around these areas, and eventually also like here. Okay, so this is what I expect to obtain. But if I don't use a resolution high enough, this mesh could eventually have polygons so big that it simply could not represent certain details, like these separations, for example, these internal void areas. Okay, so that's why in this case it's more likely that you need a high resolution rather than a low resolution simulation, which means that the calculation is going to be quite heavy. So let's activate this, and you see that actually it's running quite slow, which for the result that we are about to obtain, I think it is not worth the wait. But anyway, just so that we know what are also the limitations for these tools. I only have defined two optimization iterations. So we have the first calculation, and then we have the first optimization and the second optimization. So this is the final result. Okay, so first version, one iteration for optimization, second iteration for optimization, and final result completed in 32 seconds. Okay. So what is coming out from here are, guess what? Stress lines. Obviously, three orders of of stress lines in this case, always with the same method. So you define seeds as points inside the volume. In this case, populate 3D is enough because we have a simple box. And we have three types of stress lines. We can also separate them. We must see this in 3D actually, because we will have these are going to be the primary stress lines, which is the one that I was already expecting. Curve 2, which are the cross stress lines, and curve 3, which are basically the orthogonal to the curve 1. Actually, there is also one application that I was testing right now, because as always, as I told you, I'm investigating on how to create aesthetically valid structures, which has some structural purpose. So let's give this a second. It will show up like some kind of corals or branches that follow the structural performance of this object under these circumstances, under this load and support scenario. Let's leave it running for a while, because it's nice to see what's the result. Still calculating, it's quite heavy. Yeah, here it is. So we have this kind of coral-like system that follows exactly the stress lines. Well, actually, only one of the three outputs of the stress lines, but it's nice to have this kind of representation. I'm still investigating on this, but eventually it's going to be interesting for further development. And on the other hand, finally, which is probably the more interesting thing, we have the 3D isomesh. Now, the resolution of this mesh, meaning the amount of polygons that we have, depends, of course, on the X resolution that we set up in the Topostruct 3D model. So this value here. But you can see that once you have, well, actually, how do you determine the final aspect of this optimized topology? There are two main parameters. The first one is target density. So compared to the initial volume, which is 1, how much material you expect to have after the topological optimization. And this is 15% the initial material. Of course, if you look at this, we are not at 15% of the original body. Right? We are more or less at 1/3 or quarter of the original volume, right? This is because this is what your goal, right? But once you have the result, the 3D ISO mesh also allow tweaking an ISO contour value. So this allows, for example, to reduce or increase the amount of material around the calculated optimal shape. So you see that we still miss something here. We are close to a good solution because we already have this support here. We still need something that reaches the other load here at the tip of this beam, right? This is something that tells us that we must perform some tweaking in the settings of the simulation. So eventually, you must either increase the resolution, which is in this case, I don't think it's necessary because we already have quite a high resolution mesh as a result. But of course, you must run more optimization iteration. Okay, so in this case, if I increase this, for example, let's say I run this with 5. Now let's wait for this to run the first calculation, which is this one. And then optimization, which is a little faster than the first calculation. So optimization steps normally are faster than the first calculation. It depends much on the resolution, on the X resolution, but they should be quite fast in this case. So basically, the main observation in this millipede 3-dimensional topological optimization is that the process needs some tweaking, and it's also quite slow if you want to achieve a more precise result. And so you see that now we are getting to the tip, but everything is remaining quite filled as a volume, right? So you see that there are more details. For example, in this area, you can get to nice detail for the topology, for example. You see that when you reduce the amount of material, you go closer to the actual stress lines inside the body. And so you find out that this part is less necessary than these parts here. Of course, it depends much on the material and on other considerations, but nevertheless, you start having an idea of how things must work here. But nevertheless, it needs more tweaking than this. So we still need to work with this simulation in order to get to the desired result. While what I wanted to show you is what happens. Oh, let me deactivate this. I don't want it to run each time we open the simulation. Let me Control G, Control E. Let's switch to topos. Oh, by the way, you see this thing is remaining like active as a preview because this is something that happens with very few components actually in Grasshopper. Topostruct 3D is one of them. So I must reactivate this, Control Q, and Control E to deactivate. So its preview remains visible even if you deactivate this component while its preview is on. So you must also deactivate the preview if you don't want to see its preview on in Prime. And let's switch to Topo. I think the system is going to be the same. Yeah, it's the same, exactly 2 loads and 1 support region. There are few observations right now. Yesterday I told you, or the first day, I told you that this plugin can run on GPU mode. Actually, I am using GPU mode. But this is only possible if you have a graphic card which is capable of CUDA calculation.
Excuse me, Giancarlo.
Yeah.
You can use topos even if you don't have a CUDA graphic card?
Well, actually, yes, you can. You go into the model building and switch from GPU to CPU. It's going to be a little slower, of course, but you avoid the problem of the CUDA graphic card. It's a little bit slower, right? So one of the advantages of working with topos is that you can use the GPU, which is faster, as you know. There are few plugins that are already let's say, capable of using the GPU. One, for example, is an alternative to Kangaroo, which is called Grasshopper. which is another plugin for physical simulation. And it only works with GPU. In that case, you cannot use CPU anymore. So while Topos allows switching from GPU to CPU, but if it's possible, I do recommend that you work with GPU. And in that case, if you go into Topos toolbar, you will find there is a specific component, which is this one, that allows to test the GPU. So if Topos is recognizing the GPU and is capable of using it, you see it immediately from this component here. So eventually it gives you an error if it's not capable of working with the GPU. So this is just for testing, okay, and to free up memory in case you want to free up GPU or graphic card memory from any other processes before running the simulation in Topos. So just click this button here. As regards the building the system, it's always the same. You have boundary region and boundary conditions, which encompass the loads and support in this case. So they both converge into these boundary conditions. So there is no, let's say, loads and supports separated. One tricky aspect is that you have to graft everything. In order to avoid, let's say, the same system to be calculated several times under different circumstances or different boundary conditions, you must graft everything. So you will hover with the mouse over, for example, domain mesh S3, and then you have a density value S3, and everything here is S3. Also this one. So also this one here are also S3. So pay attention, don't ever, let's say, feed these inputs with a list, always a data tree. So that's why you see all this graft, and also this graft here and graft here, okay? And another thing is, even if you are working with boxes, don't use, for example, a mesh box conversion. So mesh box is actually a component that allows converting any box into a mesh box, as you can see, defining the resolution in the X, Y, and Z directions. Don't do this because I think this is a topological problem, because Rhino itself is not capable of handling solid meshes made up only of quad polygons. So I think this is the problem, because if you do that, if you convert these boxes into meshes using the mesh box, you will have some weird behavior during the simulation. So always use, in this case, mesh BREP. Okay, so even if they are boxes, simple boxes, don't use mesh boxes. Use this mesh BREP conversion. Yep. So, I mean, this is pretty normal. You define loads, you define supports, and etc. etc. You define the resolution of your system, which, remember, affects the final resolution of the mesh, the result mesh. And you build the model. Evaluate eventually the model statistics. This is not mandatory, as you can see. This is just an idea of what happens inside your model if you want. And then you run the simulation, which is this Optimist Solver that you have here. Yeah, you have several type of solvers, but this is for optimization. Okay. So the important thing here is the options, the parameters for the optimization. This is the number of iterations that you want to perform during the optimization process, and this is the desired volume that you want to have as target, which is exactly what we already saw in Millipede a few seconds ago, basically. And then there is reset simulation and run simulation. Fortunately, differently from Kangaroo, you can run the simulation when the simulation reaches the end, the final iterations. This goes back to false automatically. So you don't have to worry that this stays open to calculation, whatever change you make here. You can change whatever, but until you push or switch this toggle to true, nothing happens in terms of calculation. And calculation can be quite time-consuming in this case. So everything is ready. I'm going to show you, there are many outputs here, as you can see. I want to concentrate a little on the mesh output. Initially, you see this is a quite weird mesh, but it doesn't matter because it's going to get optimized. It also misses a quad here, or two triangles. And there is some self-intersecting vertices that are basically like very bad to observe. But anyway, once you start running the simulation, these things will disappear. So don't worry about this. This is compliance is basically a value, a number. There is here a quick graph that will give you an idea of the evolution of the optimization process. And you will see that there will be a line here appearing that will dance around up and down, and then it will stabilize according to the compliance of the result with the desired condition. But you will see this in a while. So let's run the simulation. Here you have the number of iterations that are already being calculated. We must reach 25 because that was the amount of iterations that I defined. So here it is, the resolution. You see that actually the final optimization is quite compliant because the value is high. Number of iteration is 25, so it's respected. Here you have a monitor of what happens inside each iteration. So you see it reaches up to 25. It tells you what operation was doing, how much time it lasted. Okay, so here you have a monitor of the situation. And this is the low-res version. So it's this ISO mesh here. Once again, you have the ISO value. You can decide how much, how close you want to be with respect to the desired target density. There is also a deflection control if you want to see how this thing is going to deform eventually, or what is the tendency to deform of this object. You might notice, well, actually these weird triangles stayed in place, which is something that we can solve by increasing the resolution. Eventually, you might notice something like this. Even if we have used a very symmetrical situation, as you can see. So everything is symmetrical with respect to the x-axis. So there is no particular reason for this object to come up like shifted, like on the top of this system configuration, and having this kind of curvature like this. And this is because the resolution is quite low. So if you let me double check. Yes, if we take a look at, let me hide also the mesh. Let me go back to the top view. Well, in the top view, we don't see the blue arrows, but yes, in the right viewport, yes. So if you take a look at these arrows, if compared to the actual volume, you see that they are all displaced to the right. This is because of the resolution. So we are basically considering only those nodes that fall inside the intersection between this load mesh, this load volume, and the boundary volume. Okay. So in this case, if you want a more precise representation, I would recommend that you increase the resolution of the system, and so you have a more evenly distributed load and along the thickness of this object. And the higher you go, the more evenly you can distribute loads and have a more symmetrical result. Of course, you pay this in terms of calculation time. So you see that it went back to false when it stopped calculating. It basically reset the simulation because of the change in resolution. You see that everything has become very slow, even just the reset. And let's run this. Don't worry about the Catmull-Clark being red. It depends on the fact that the initial values, the initial solution for the ISO mesh might be a very weird mesh. But as the iterations go on and on, you will see that the mesh, the ISO mesh stabilizes, and the Catmull-Clark as well tends to produce let's say, smooth mesh result. And you see that with the proper mesh resolution or target X resolution, we start to get quite an interesting topological optimization for this body. Each of these stages here of the simulation, it's a work in progress, actually. You cannot go back to this phase here. So this is iteration number 11. You cannot go back to iteration number 11. But if you detect a shape in an intermediate iteration, you can simply limit the amount of iteration and get to that result. The problem is that if you stop the process like at this point, at this stage, you will not be working with a total optimization. It's an intermediate phase. Okay, so the more iterations, the best result you get. Also, in general, I mean, iteration number 25 that we are going to reach quite well soon, more or less, it's going to be worse than iteration 50. So if you have the time, I do recommend that you leave this topological optimization processes running, especially if you have some time out from work or so on. You leave the computer calculating and then see what's the final result. So don't stop the optimization process, because some things happens only with high values of iterations. Like, for example, this part here has been detected at iteration number 18, as well as this one. So these details only happen when you leave this thing running and running and running. So 22, we still have some refinement going on. We still have 2 iterations to go. But you see that it's easier to work with topos with respect to millipede in order to have a proper topological optimization. So 25, I think we are done. So now we see that it's a pretty symmetrical result due to the high resolution. Also, having a high resolution, the optimization process is capable of better understanding where the stress line are determining the necessity of material and where there is no need for a specific material density. You know, and in the end, you always have the ISO value here. That in this case, you see it's pretty. It works like inversely proportional. Lower values produce a thicker mesh. Higher values produce a thinner mesh. So if I take this value here and increase it, you see that the mesh is getting thinner. So material tends to disappear. And you can also get to a very elegant yet thin and eventually too thin structure. Okay, but you can play with this because this is always respecting the stress lines. Or the opposite, you can go lower values and fatten this this mesh. And in this case, you see that there are also some rigidity connection here at the bottom, and also inside the body of this part. And in the end, you can run some smoothing algorithm in order to have a more pleasant aspect for this object, and we can see this as the final result. Normally, I do recommend that when you do this kind of analysis here, and you bake something, especially if you bake the mesh, group it, because you never know if the mesh is made up of one single piece or several pieces. So group it so you can eventually select it automatically with one click. And also pay attention when you bake these objects here. If you see that the object is baked more or less immediately, it means that it's made up of valid meshes. If you bake this and you, after a while, a window pops up asking if you want to bake invalid object or invalid meshes, in that case, it's up to you. You can bake them and you have it available in Rhino, but these are problematic meshes. So you might want to double check their integrity or their topology with some mesh analysis program, like Mesh Mixer or something like that. Because in that case, if you have an invalid mesh, it's more likely that you are not going to be able to produce at least this kind of parts. And you can see what's the final result of this topological optimization is this kind of nice organic shape optimized for the load condition that we specified, like a load here, and support in this area. There is always some deformation analysis as well, that you can see, but remember that it's just like a visual deformation analysis. You don't know from this thing, you don't know how exactly the object is going to behave really. So if you increase this value, you see how the object should deform under these circumstances. For example, if the load exceeds the material capabilities of resisting to the deformation. Okay? But we have, in this case, we are not considering exactly some specific properties. So when you define, for example, here, the only thing that you can do as regard the boundary domain, which is basically the original body, is the density value, is the Young modulus that allows to define more or less the general properties, the general behavior of the material. And you have the Poisson factor also. Poisson factor is something that that it's important if you want to get to a more realistic behavior for a material. You saw that Poisson factor doesn't show up, for example, in kangaroo. So it's something that it's good to have it here. And why? Remember that this Young model in gigapascal says that this is 210. It means this is a, if I don't remember wrong, in our, well, we can simply reopen the kangaroo Young modulus, where we already had it in gigapascal. And so 210 is iron. Okay. So if it's iron, this deformation, I think it's quite unreal, of course. Okay, you should apply a huge load in order to have this kind of deformation. But this gives you an idea of how the body or the part will behave according to this load condition. Okay, you can play around with topos because it's basically limitless, as it relies on a mesh brep conversion. For example, we can also stress test this as the last example. I'm going to turn this off. This is the actual low resolution mesh coming from the simulation. Oh, and by the way, here are the nodes inside the mesh object. Actually, these are already the nodes coming from the optimization process, of course. And so this component here is the principal stress component. So you have all the values at the different level for each different node inside the structure. So if you are interested in having the numbers, here are the numbers. Then there are some different visualization. This is basically the relevant or the resistant nodes, like represented with this kind of mesh visualization, like this, like dots. This is basically the same, but with some gradient. So you see there are three different representations of this of the resistant part of our body. It's basically, with this one, you simply define always, once again, the ISO. So the lower, the thicker, and the higher, the thinner. So if you want to concentrate more on the resisting part, more close to the stress line, you increase the ISO value. Okay. And then the move simply displaces the next two copies away from the first one in order to separate them. This is not useful, let's say so. So it's just for visual analysis in order to understand what happens inside your body, your boundary volume in a visual representation. And this is the monitor, as you see. It's just monitoring the operations with all the parameters that affect the operation itself. So I want to use this thing, and first of all, let me also deactivate this eventually. So in order to try to avoid any possible problem. So yeah, now we are good. I don't know what happened with the dome. Eventually there is something that is not properly, let's let's say, understandable in terms of how I created that object. So if we have these, I want to take this this object and apply a load. For example, let's create a new load region, like place it here on top, and also from the top view, I'm going to apply another load region like here, and I want just one support here at the bottom. So I'm going to create a box in this area. I don't care too much about the size and position, but this is more or less what I want to try. So let's also brep, set multiple brep. These are going to be the load region. So I'm going to substitute the actual load region. And I'm going to take another brep component and take the support region and substitute it like here. Okay, so let me also internalize all of these so we can get rid of geometry in Rhino. And let's see what happens if I reactivate this. Yeah, I think it's working. See that we already have the loads and support nodes already showing up correctly. So let me also activate this. You already see that we have this kind of, well, it's quite low resolution if you think about it, because we have an organic shape right now, but we cannot avoid this kind of, let's say, aliasing of the edges. The only way that you can solve this is by increasing the X resolution, but I won't do this right now because that is going to be way too slow. We already have 60 and 25 iterations, so let's play fair. And let's reset, and let's move to another point of view, and let's run this. Let's see what happens. Normally, if Topos cannot calculate something, or there is some thing that is not perfectly understandable, it warns you. It warns you in which way. You see that here the result only shows a few values. It says the optimization is already over in no time, and here you don't see any progress, any lines. Oh, by the way, you see that this thing is like this weird because we have a deflection of 3.55. So that's why you see this thing. But I don't know if it's possible to tweak this in real time. Let me double check. I forgot to bring this back to 0. I think we have to wait for the iterations to finish. But you see that things are already in progress. And still, I think I also made another little mistake, which is I didn't change the material. So I'm still considering like a iron wall, which is somehow less probable than something like, I don't know, concrete or whatever. Also, I'm not considering the value of the nodes, right? So it's totally, let's say, hypothetical, this study that we are running. But we already see something that it was perfectly understandable. We have some stress flowing from the load area to the support area in the two region. And this is also happening according to the curvature of our slab. So it's, oh yeah, I think I finally can bring this back to 0. Let's see. It reacted quite slowly, but it reacted. Keep in mind that the optimization calculation is quite heavy and quite resource consuming. So it's very difficult that you can do this kind of changes on the fly on other parameters. Yeah, so this is the undeformed version of our system. So in the meanwhile, while we wait for this thing to finish, if you have observation or questions, we can already start discussing this. I think this is pretty straightforward. As you can see, you can apply to any geometry. I don't know exactly why the dome didn't work. I will eventually double check what happens in case it needs some specific geometry condition or something like that. And eventually I will come up with a solution. But
can I?
yes, of course, Andrei.
Okay. In previous examples with those boxes,
Yes.
first with Millipede and the second one with Topos, do you have a similar assumption? Similar start data? Because
yes.
Because we have a completely different result.
Well, actually, I think it's my bad. Eventually, I didn't express myself correctly. But the problem with Millipede is that in order to get to a good result, remember that Millipede is quite old. Maybe it's not as efficient as Topos. In case of Millipede, you have to increase the amount of iterations quite a lot in order to start having a proper result, final result. So in general, yes, the result that we were getting is quite different, but it's just because of the number of iterations that we didn't adjust in Millipede. In Topos, it's quite more precise and faster. So it definitely, for three-dimensional topological optimization, I would recommend that you use Topos and not Millipede.
Okay.
Yeah. But
So,
Topos, the only thing that you can do with Topos is this one. You can do topological optimization. While with Millipede, you can still perform structural analysis as we got frames and shells in a very efficient way.
Okay.
This topological optimization, I see applications more in product design or product engineering more than architecture, honestly, because these kind of shapes they are optimized in terms of performance, but not they are not made exactly for being manufactured or created at the architectural scale. So in that case, once again, I would recommend that you take a look at Peregrine.
You know, I'm thinking about formwork for
Yes.
concrete 3D printing.
Yes, but concrete 3D printing, hypothetically speaking, doesn't require formwork. So the interesting thing is that,
yes, concrete 3D printing is a lost formwork.
Well, yes, you can see it like that, but you can also directly 3D print concrete. So in that case, you can can also avoid completely that passage, you know, that step. But the problem is that it becomes quite expensive. However you want to produce these kind of things, it becomes quite expensive. And also remember that concrete 3D printing actually only allows some very specific, let's say, shapes, you know, because you have to think about the performance of the built object. And we are not close to the actual performance of casted concrete. There are so many problems still to be solved. So yes, it's an interesting investigation field, but I think we are not close to the final solution. Yeah.
Mm-hmm. No, because with the Topos form is more interesting than the Millipede form.
Of course.
When we are looking for form finding.
Yeah, the term form finding, it's a little ambiguous, because in this case form finding can be seen as topological optimization, but form finding is also the process that we were running in simply in Kangaroo to determine the catenary shape. So form finding is basically deriving the shape of something according to some external condition or physical properties or boundary condition like loads and support. So everything is form finding in the end. So in this case, it's evident what's the meaning. But yes, Topos, I think it's extremely powerful and promising. Also, I really hope they are going to further develop this tool, because there are many things that that can derive from this kind of study. And also, it's more precise. It's absolutely more precise than Millipede. So this kind of shapes and optimization is way better than the one that we were getting from Millipede, especially if we think about the smoother version that we are seeing right now.